kind of got started on this topic last time. This is the very beginning of chapter 13. And I don't know if you guys were paying attention to the video that was on, but they were talking about graphing vector valued functions by plotting points. What I'd like to do is have you guys get more used to using technology to try to graph these things, and for that we're going to take a closer look at vector valued functions using that program. A program that you can get online. So last time we pulled out this program and tried to plot some surfaces using implicit plot, I think it's called. So this time we're going to use parametric curves. Maybe I should have ran this earlier. So let's take a look at that that spring that we discussed last time. We only talked about a couple of things last time, I think, in terms of getting started, and they both had a circular x and y. So x and y are circle-looking things, and then there's one where it just had a 1/2 t or something like that, and then there's one where I put a trig function in there. So in this graphing program, to graph a parametric curve in space, you want to add a space curve. So let's add a space curve. And here, it's kind of set up here already to go with a cosine and a sine, and then this is a 0.1t. I think let's do a 0.1t. Let's take a look at that. Graph it. So in this program, you want to get rid of graphs. You want to make sure that we're not dealing with functions yet. So just make sure it's not selected. And this button over here says clear graph. And then let's try to graph this again. Graph. So here's a graph. They kind of color coordinate it so that the color is kind of based on the height. As the height changes, the color changes. I think that's how they colored it. Or maybe they colored it according to t. Never mind. I think they're coloring it according to the t-axis. So this has a default box around it. If you want to change something in terms of how the graph might look like, you can go to View Settings, and then I think we can get rid of the box around that, so we can just look at the graph itself. And then you can show orientation arrows, because when you're looking at a graph that's parameterized by some t value, as t increases, this thing goes in a specific direction. And we'll see later on that the direction is going to be important for us. So you can show orientation arrows so that you can see which way the graph is going. And then we can also trace and animate to look at how the graph is being drawn for different values of t. And then you can take a look at it from different points of views and do the animation again. So it looks like we're not directly on top of this, but a little bit off of the very top. You can see the circular motion that it's making on the xy plane. And then how you can see the z increase as you go up. All right, so the other graph that we threw in here was sine or cosine, and then I changed the amplitude so that you can go through and finish a couple of rounds of this by the time it goes to 2 pi. or in this case, they're going to 10, so this thing will just repeat itself. So let's take a look at that. Maybe let's just go from 0 to 10. I might reduce some of the colors. You can still see the arrows. And then we can take a look at an animation of it going around. You can see how many times it went around. 10 is a little bit bigger than 6.28, which is 2 pi. So it does a little bit more than half of the, or one full circle. It does a little bit more than one full circle. Okay? So if for some reason you close this window, you can still see the graph there. You can always recover that window by selecting add a space curve, and then it'll open up that window again. It's the same window that we've been working with. If we throw in a number that's not divisible by 2 pi, I wonder if this is going to work. Let's see. Oh, it's still going to be smooth. I was wondering if it was going to break apart. So sometimes I put a pi in front of the t here to make that period not exactly fit in to the current period. And so if you look at the animation, when it starts to make that second round, it's a little bit off. And so this would be interesting if we go make our t really large, like 30. And we might need to make our steps a little bit larger too. Let's maybe go 200. So if you look at it from the top, it's still that circle, the x squared, the x and the y. It's still the sine and the cosine. But now it changes, so trace t equals, let's just animate. So it keeps going around, but it doesn't repeat itself anymore. So that makes an interesting kind of looking graph. So you can play around with this, changing the values of the x, the y, and the z. If you just want to look at circular things, just keep the x and the y the same, and then change the z and see what happens. But you can definitely change x and y as well. All right? Has anybody pulled this up yet and tried it? No. The graphing calculator? Yeah, so much easier. All right. So one of your homework problems kind of looks like this. We have a bunch of graphs, and then they ask us to select which one of these would fit in the graph. And so this would be something where you can try to visualize it, try to imagine how this thing might look like in terms of the x and then the y and then the z, and then try to imagine how it would match up. Of course, if that gets a little difficult, which it might, you would probably want to graph it using some sort of technology. But let's get started with that. Let's do that for our first thing we do in this class. So let's first analyze it without the graph, and then we'll imagine how it would look like. Well, let's try doing it without the graph. Let's analyze the x and the y and the z, how it might look like, and then after that, actually graph it to make sure that what we're doing kind of makes sense. Let's take a look at the first one. You got x is e to the t cosine 7t, e to the t sine 7t, and an e to the negative t. So e to the negative t, what's that graph look like? So if I say y equals e to the negative x, and you were to do a quick sketch of that graph in your head, how would that graph look like? It's an exponential function, and it decreases, so it's an exponential decay. So this thing's going to go down. And it being in front of the sine and the cosine for your x and the y means that's kind of like your amplitude. So this is going to draw circles, but it's going to draw circles going down. So just for the x and the y, I would imagine that this thing would be kind of like a spiral going down. So that's the view from the top. And now you have e to the negative t again for your z, which means it starts off, maybe we can start off with t is equal to 0, but you know we don't always have to start off with t is equal to 0. But starting off with t is equal to 0, it looks like your height is going to be going down, but it'll never reach the origin. So imagine from the top view, you're going in a, I guess I would be starting with x is positive 1 here. You'd be going in a counterclockwise direction and spiraling downward. And then if you put negative numbers in, then you're spiraling upward. So this looks like it's a spiral that's going down. Can we agree on that? All right. You see how I kind of analyzed that graph? I looked at the main parts of it, the sine and the cosine, and then the e to the negative t is in front of the sine and the cosine, which kind of controls its amplitude. So from a circle point of view, it kind of controls the distance from the origin of the circle. All right, so that's the first one. Now let's take a look at the second graph. We have x is equal to t, y is equal to 1 over t, 1 over 1 plus t squared, and z is equal to t squared. Oh boy. All right. So x equals to t is just a linear function. Do you know what y equal to 1 over 1 plus t squared looks like? Do you know what 1 over 1 plus t squared looks like? It's the what? Well, the integral of this is a tangent inverse, but it itself is not necessarily a tangent inverse. Like what? Does it have an asymptote at 0? Like, could I put 0 in for t? Would it be undefined if I put 0? No. Asymptote at 1. Wait, when you say asymptote, do you guys mean horizontal or vertical? Horizontal asymptote? So that means as t goes off to infinity, where is this going to go to? 0. It's going to go to 0. And when t is equal to 0, what's the value? 1. So you put 0 in for t. So I think this graph is going to be like a bell shape. It's not your typical bell-shaped curve, but it's kind of like bell-shaped. And I put this pointy, but I think it's smooth up here. And then this is just a parabola. So, boy, let's see if we can put all this stuff together. Just by plotting 0, we get 0, 1, 0 when t is equal to 0. So 0, 1, 0 is on the y-axis here. Now, the thing about this on the y-axis is that if you look at this from the y-axis point of view, it looks like it's, and on the x and y axis point of view, it looks like the x is going to go from negative to positive just like a regular t value. So that makes this parameter t kind of look nice and easy. And then it would go up here and then come back down. This is kind of flat. That's not the graph that I really want, though, because this thing is going to start when z is positive and come down to 0 and come back up when z is negative. So maybe I'll redraw this graph as a shadow on the xy plane. But then what's really happening is that above that it's up higher, and then it goes down, and then it comes back up high. Something like that. Where the shadow that it makes is on the xy plane. Okay. C is something that we did already. It's that crown thing. It looks like a wavy thing around. So let's skip over that. Let's take a look at D. Let's take a look at D. It looks like the sine and the cosine is happening, but it's not on the x and y. Instead, it's on the x and the z. So it looks like maybe on the x and the z axis, we would be looking at this circle business. But again, it's just a circle as a shadow on the x and the z axis. But what's happening along the y is that it's going to be an increasing value in the y. So what do you think this is going to look like? A spring, but it's sideways. It's opening along the z or the y. So the sine and the cosine, maybe when t is equal to 0 might be a good place to figure out where a starting point of this would be. When t is equal to 0, cosine of 0 is 1, and the sine of 0 is 0. So it's starting here on this axis, and then it's going to go in a counterclockwise direction if you're looking at it from the x and a z point of view. What's that mean? Going this way. And then it's going to increase in the y, so it's going to be your spiral on the y. But then the shadow that it makes, if we look at the shadow on the xz plane, it will just be that circle again. No, I think I meant to draw that in green. Not that it matters. All right. Well, let's take a look at these ones that we've done so far, and just take a look at the graphs of these, and then we can figure out the others just by graphing it. So I think it would be good exercise to practice imagining how it would look like in the graph. But for most cases, it'll probably be good to be able to use a computer calculator. Now, you won't have a computer during the test, so I probably won't ask you to graph these things, but I might be able to ask you to describe these graphs if I have, pieces of circles around and stuff. Or maybe I might ask you to come up with an equation that describes something that I have, or maybe I would graph something and say, try to find an equation for this. All right, let's take a look at the first one with the e to the t. take a look at this graph. So this graph didn't really give me much information here because I'm going, so another part of being able to graph things properly is to really use the information that you have and then use it correctly. Since this is an exponential function, it's going to shrink down exponentially. So you may need to view it, a little bit differently because it's going to shrink down really quickly. So maybe instead of going from 0 to 30, I just need to go from 0 to 5. Let's keep the number of steps at 100. Let's graph it. Still can't see very well. Actually makes it worse. Let's go from negative 5 to 5. So again, because of the exponential nature, it goes to infinity really quickly and it goes to 0 really quickly. So it's hard to see, it's hard to view this, but we may need to exaggerate this a little bit more by blowing it up. So you can try to zoom in. And as you zoom in, you can kind of see it being wrapped around. And I stopped at 5, but maybe this time I'll go all the way up to 10. And then keep zooming in. Oh, maybe I can't zoom in anymore. So sometimes you might need to use the zoom in tool to see how it would look like because it's so small. But I think what we have written down here, what we have drawn here on this graph looks like an exaggerated version of it. It looks like a spiral. All right, let's take a look at the next one. And the next one is, let's see, t one divided by, and when you're dividing, when you have fractions, you have to make sure you use parentheses, especially if you're adding and subtracting things. So you have to know your order of operations. And then the last one is t squared. Let's go from negative 2 to 2, maybe for starters. And then let's graph it. So here's that. If you look at it from the top, it looks like that shape, that bell-shaped curve. And then if I move this back over here, the z values go up on either side. So that kind of mimics what I drew here earlier. So that looks good. All right. You guys got the idea? Let's do that other one. Let's do one that we didn't draw. We didn't draw E or F. What would you be interested in seeing? Yeah, because E has a sine and cosine again, right? So let's take a look at F. So x is equal to t, y is equal to t squared, and z is equal to e to the negative t. Let's go from, there's another e exponential function here. Let's just maybe go to 5 and graph it. I don't know, it's hard to see this. Let's try to animate, trace it. Let's try to zoom in or zoom out maybe. And then animate and trace again. Let's take a look at the view from sideways. Sometimes if you get a handle on this, it's hard to control how you rotate it. There you go. So x is pointing to the left, z is pointing straight up, and y is kind of going towards you. And let's take a look at the animation again. Okay. So the z is, it's really subtle here and really hard to visualize. But the z is an exponential function, e to the negative x, or e to the negative t. And you know that that never is going to hit the axis, the z-axis. So this thing, it looks like it keeps going down, but technically it never hits the xy plane. And then, in fact, if we draw the xy plane, let me draw the xy plane. Z is equal to 0 is the xy plane. Can we make the xy plane bigger? No, it's hard to. Well, anyways, you can mess around with this and check some buttons, some check boxes, animate, and change some parameters to see how this would look like, and try to imagine how it would be. All right. So if I was answering this question here, we have some of these graphs I kind of identified already. We have the spiral that's decreasing is 2. We have this parabola going up and going down and making that shape. That's our second one. IV. We have sine, cosine, and then another sine function with a different amplitude. That's BI. We got sine, cosine going sideways. That's 3. Sine, cosine, and then an ln. So from the top, it looks like it's a circle. That looks like a V over here, and that's the 5th graph. And then the last one we just did kind of looks like this. This graph that goes down here, and then it kind of has an asymptote on the xy plane. That's the first one. Okay. So try to do, when you're doing this problem, I think you're going to get the same thing. They're not going to vary this very much. But when you're asked to kind of do a multiple choice or a matching problem like this, what you want to do is try to, without looking at any of the pictures, try to imagine how these things would look like based on the equations that you're given on the x, the y, and the z. And then once you got a general idea of how it should look like, see if those ideas kind of match with the ideas with the graphs that they have. Okay. All right. So that's the graphing business. The next thing I want to do is I want to take a look at derivatives of these vector valued functions. So let's take a look at the third one. The one that has 3 for the answer, D. Let's take a look at this example, and we know how the graph looks like, right? So it looks like a spiral or a spring. By the way, this is, you guys know what this is actually called? Mathematical term. This is called a helix. What? If you look at the DNA helix, it's like a connected spiral thing. So this is called a helix, and it is basically a shape of a spring. So people may be interested in taking a look at this as a path of something. So you can imagine that this might be like a roller coaster or something like that. Actually, this is kind of going sideways, so it'd be like a loop roller coaster. So we can imagine that this is some sort of roller coaster in the path. And the path can be given by, if we take a look at this from a vector point of view, then we kind of write the vector with an ijk, or with parentheses and commas in between as components. And so we drop the idea of the x, the y, the z because they live in their own components here. Now, I might be interested in a derivative of something. They're functions here, and we've taken calculus already, Calc 1, and so whenever we see a function, we're in the calculus class, we really want to take a derivative of it. So we can take the derivative of this, and basically the derivative of a vector-valued function is a derivative of each of those components. So we're basically taking x prime of t and then replacing our x component with the derivative of that. So I think this would be negative 4 cosine of 4t. Make that sine. The derivative of the next one is just 1. The derivative of the last one is 4 cosine 4t. So we have a new vector-valued function, and the curious idea is that what is this new vector-valued function? So let's imagine our position function being your position. Our original vector-valued function is a position. So that tells us where we are for a specific value of t. I'm just picking random values. T is equal to 0, t is equal to pi over 8. Just randomly picking values. So the question is, what is this? Well, I think that'll give us that part as a direction vector. But more specifically, you know that in physics that if you have a position, you take the derivative of position, what do you get? You get velocity. So in fact, what you get here is a velocity vector. So much like the derivative in Calc 1, when we take the derivative of a function, it's a general derivative at any point, right? So if we want the slope of the tangent line at a specific point, or if we want the velocity at a specific time, we want to find the derivative, and we want to input a specific value for the time. Okay? So this is a velocity vector at any time t. Now, if I want to find the velocity vector at specific time slots, I can just put in those values of time. So when t equals 0, for example, r prime of 0 becomes, this would be 0, 1, 4. And at r prime I put pi over 8. I don't know if this is going to end up being a nice value, but let's see. When t is equal to pi over 8, we got r prime of pi over 8 is equal to, so what's sine of 4 is pi over 2. Yeah, so this is what is it? Negative 4 times sine of pi. What's sine of pi over 2? 1. Negative 4. So that's negative 4. And I have 1, that there's no t values to put in here. And now I have cosine of pi over 4, which is 0. So the question is, what are these vectors? Well, they're velocity vectors, right? What does that mean to be a velocity vector? So, can I draw a vector here, I wonder? Let's redraw this helix in our graphing program. I'm going to take that function out again, and where's that space curve? And this is a cosine of 4t, was it?
Yeah, the original cosine 4t, y equals sine.
And then let's go from, let's say, negative 2. 2 pi is probably too big, so let's just go to pi, like 3.1. And let's graph it first. So it looks like that. Let's zoom in a little bit so we can see nicer. Let's zoom out a little bit. Looks like that. And if we animate it, we can see it being drawn out, going in a forward direction. So if we fix it maybe at t is equal to 0, we're at that point over here. And when t is equal to pi over 8, we're at this point up here. So, can I draw a vector? Graph. Add a vector. So let's add a vector. The vector that we want to add is, what's that first vector that we had at t is equal to 0? 0, 1, 4. So let's draw this in red. So if I were to draw this vector, I would get this vector that looks like that. Let me put the point at 0 again. I don't know if you could see it, but this vector right now coming from the origin looks like this. It doesn't look like it touches the curve anywhere. So what does this actually mean with respect to the curve, I wonder? So what's happening here is that this is not a useful vector if it's just a vector as we see it as, what is it, 0, 0, 1, 4. Right now it's kind of pointless. It doesn't do anything for us. But that's what the vector is. But if we take that vector, remember vector is just something with a direction and magnitude, and it could be placed anywhere. So what if instead of having the initial point at 0, 0, 0, I move that vector to where my point is on the graph right now? Where is that point on the graph? I think it's at 1, 0, 0, right? So if you take a look at your R value, when R is equal to 0, you put 0 in here, you get 1, 0, and 0. So let's do that. Let's put that vector and have the initial point at 1, 0, 0. So now I have that vector. Does this vector make a little bit more sense than the first one?
Well, since you tangent the point.
That vector is tangent to the curve at that point. And that's not a coincidence. That's the velocity vector. And it's actually tangent to the curve. You see that? You see how cool that is? No? Can we make it any cooler? I don't know. All right. So that first vector is actually tangent. Let's add another vector. Let's move this at pi over 8. So now we're up here. And then now we have another vector. The other vector is do you remember what it was? It was negative 4, 1, 0. But this time, let's move the point somewhere else. The initial point. Where should the initial point be? So look at your function, r, the original one, and put pi over 8 in for t. Pi over 8. 0, pi over 8, and 1. So if you have that as a starting point, you'll see that the next vector, which we'll draw in blue, green, green, will be tangent to that curve at that point. So it's not a coincidence. It's actually what's happening. So what's actually happening here is at t equals 0, you're at this point 1, 0, 0, and then this red vector that's drawn here is that vector that we found. It's the velocity vector at that point. And at this point over here, where t is equal to pi over 8, you're at the point pi over 8. You're at the point, where are you? 0, pi over 8, and 1. So that's the point. And then now your direction vector over here, your velocity vector, is the derivative of the position evaluated at pi over 8. All right. Any questions? What's pi over 8 approximately? Can somebody punch that into their calculators? 0.39. So let's put this in a scenario now. Let's say we have, I'm just thinking up of a word problem right now. So let's say you had a roller coaster that's going here, and then at some time that's a little bit past 0.39, your seatbelt came off, and then you flew off the roller coaster. And then you started going in a straight line direction. So the question is, when are you going to hit the floor, the XY plane? So the way this is set up, it looks like it goes below the XY plane because of where the helix is. We could change it so that it goes up, or we can just leave it the way it is. But I'm thinking about a roller coaster problem now for a test or a quiz. So let's make it up. So try to see what I'm doing here. I'm making up a problem, and then what I want to do is I want to try to figure out where something goes off of a curve. It's going to fly off at a tangent. And so when it flies off at a tangent, you got to think of a velocity vector. And when you think of velocity vector, you got to think of the derivative. So now at some point you flew off, you're going to follow a straight line path, right? So this problem is now going to involve you coming up with an equation of a straight line in space. So what do you need for an equation of a line? Point and a what? And a direction. You need a point and a direction. We have the point where your seatbelt fell off of the roller coaster, and then you have the direction that you're going to move tangent to the roller coaster, right? So you have an equation of a line from there. And now from that new equation of the line, where are you going to hit the floor? The floor is the XY plane. How are you going to solve for that? What? Z is equal to 0. And so you'll figure that out. All right? All right, let's make up the problem. So suppose you're on a roller coaster. With path. What was the path again? R of t equals cosine 4t, t, and sine 4t. Okay? The ride technician did not buckle your belt correctly. And at t is equal to Is it 0.38? 0.39. So I'm going to go a little bit past that. Let's say 0.42. You fly off the coaster in a line. So you fly off the roller coaster. So when would you hit the ground? Maybe. Maybe you might just be injured. Well, this guy, the ride technician, probably got sued. Who's the ride technician? All right. So, some guy named Ray. All right. So we kind of got the picture idea for this. Now, if I was doing this, I probably would have spent a little bit more time trying to think about the time in seconds so that it's like instead of 0.42, this would be 0.5 seconds. I probably would have lifted the roller coaster up higher. How would I lift the roller coaster up higher? No, close? No? So if I add a constant to the z component, then this roller coaster will go up higher. Should we make it go up higher? Let's make it go up higher. What are we going to add to it? So the roller coaster is just, looking at the sine and the cosine, the roller coaster is just 1, has amplitude 1. So if I move this 1 up, then the bottom of the roller coaster would actually be on the ground. So do we want to go there or do we want to go up higher? Let's go up higher because it'll hurt more. So I'll put 5 there. Okay, and so I'd probably use appropriate units too, like feet or meters. If I'm using feet or meters, then I'll adjust. I would have adjusted the amplitude, and again adjusted the coefficients and stuff. But we'll go from here. All right. I guess it might be good to first take a look at the graph of this. And for this, I'm going to jump to the graphing calculator to make it a little bit easier for me, because I can adjust the views a little bit quicker on this. So the first thing I want is to take a look at this graph, cosine 4t, t, sine 4t. This is going to give me the graph from 0 to 1. This is all I really care about. Oh, I added 5 to it, right? Whoa, now you can't see. Let's make the z go from -1 to, I need 5 plus 1, 6. So I'll go 7, -1 to 7. And then I don't need this much, but I'll make the t go from 0 to maybe 4. So this is how my graph looks like so far. And I want to know what happens at t is equal to I'll call it a for now. A equals to, what is it? 0.42. So what I want to do is I want to see where that point is. So I'm going to replace t with 0.42. that gives me some point over here. And so now let's figure out the tangent. All right, so that's what I have so far. A point on the curve. Let's figure out how the tangent is going to look like. So just a rough sketch. This is where we are so far. We can identify that point by putting in 0.42 into the function. So r of 0.42. Can you guys punch this in your calculators? What's the cosine of 4 times 0.42? And make sure you're in radians. Say it again. Negative 0.11, and then the z component is sine 4 times 0.42, and outside of that you add 5. 6. I'm wondering if I needed to go a little bit more than 0.42. So maybe 0.5. Sorry, I'm going to change it. This is what happens when you're making up a test. All right, let's try it again. What's cosine of 4 times 0.5 is a half, right? No, wait a minute. 0.5 is no good. Oh, we'll keep it at 0.42. Yeah, so this is what happens when I make up exams. I sit there and think of problems, and then I have to adjust it so that it makes sure it kind of makes sense, and then the result will come out. All right, so let's take the derivative. R prime of t, we already have the derivative, right? Negative 4 sine 4t 1, and then the 5 doesn't make a difference in the derivative for cosine 4t. And then now I want to see what happens to this when you put 0.42 in. So some calculator work again. What happens when you have 0.42? Anything? Negative 3.9. Let's go with negative 3.9. It's what? And then the cosine. Okay, so this is your other vector, and I want a vector from this point. So the way to make a vector is you have to give it a starting and ending point here. And so the ending point is, what was the derivative again? Negative 4 sine 4t. 1, and then 4 cosine 4t. So here's my vector. It's going to take a long time since the z value has a slow slope. It might take a while. So this is your point. Where's my colors? This is your point. This is your direction. And then you would have a point in a direction. You would find the equation of that line. So you would put this in an equation of a line, and then you would draw that line. And then eventually it'll hit the xy plane when you set z is equal to 0. All right? There is no acceleration due to gravity. We'll talk about that next time. So does this idea make sense? We didn't finish the problem. Do we need to finish it next time, or you guys can figure it out? All right, so why don't you guys figure it out for next time and tell me what the answer is and see what happens.